Okay, thank you very much. It's a great pleasure to give a talk here at COLT. So I'll be considering some more or less classical also questions. So the problem statement will be very familiar to all of you. So we have a very standard statistical learning framework. We have an ID sample, we have a class, we have a bounded for simplicity loss, and we are aiming to compute the excess risk, and the typical bound is of this form, and the standard question is to calculate and understand what something about the complexity. So the beta is something related to the noise rate, for example. So what is complexity and why tight bounds really matter? So for example, consider the following very naive example. We have a realizable PAC framework, and for class F1 we know that it's learnable with a rate log n over n for some ERMs. And for the second class, we know that it's learnable with the rate 1 over n by any ERM. So the question, is it important? So only the logarithmic gap? So there are 2 points of view. At first, you can look at it from the point of view of mathematics, because in empirical process, citing Michel Talagrand, you have to use some skills to remove the last parasitic factors, and generally these 1 over n are merely factors appearing due to scaling. If you are more interested in practical implications, then the class F1 is, so for this class is very complex in some sense, even it's a VC class, and active learning, for example, will not help it. And for the class F2, it's so simple in some sense, then there is an exponential convergence rate in active learning, so it's worth studying. We'll consider the Bernstein noise conditions, so we introduce the excess loss class and assume the following moment assumption for the excess loss class. And it's a very standard generalization of the Massart noise, Tsibakov noise. It holds in well-specified and the convex regression when the noise and function class is bounded. So very general approach. Of course, complexity is related in this case to Rademacher complexity. You can localize using this well-known result. However, there are several problems. When we are doing symmetrization, plus minus ones, then it's difficult to take into account the distribution of px. We're working with empirical entropies. So difficult to prove minimax lower bounds, and the original papers usually need star-shapedness and convexity assumptions for applying these techniques, and they're not very favorable for example, classification problems. So the complexity measure which we'll discuss is so-called doubling dimension or local entropy. So consider the covering number with respect to L1 first, then denote the ball of radius epsilon by this, and now we are just trying to intersect the class with the ball of radius 2 gamma and try to cover it with balls of radius gamma. So it's green, we are covering the green circle by smaller circles. And we define 2 fixed points depending on beta and k. So the first one will be about covering with balls, and the second will be about the covering with bracketing, so bracketing numbers. So we're covering with brackets instead of balls. And we sign it with a symbol bracket. And one of the theorems is that, which we prove, that if we're in this bounded scenario on Bernstein, if we are able to select several functions f1, etc., capital N, such that the loss class forms a covering of the loss class with respect to L1, so we can choose somehow, depending on the parameter eta, the radius of the covering, such that the ERM which we run on this net will have these learning guarantees. So, and if you're not satisfied with learning on some epsilon nets, then you can just write down this for ERM, but the price will be that you replace the entropy to the entropy with brackets. So several problems are directly solved by this result. For example, if you consider the homogeneous half spaces under isotropic long concave distributions, so there are so this example took a lot of attention, and for example in a realizable case, and there are some results under general Bernstein noise, but so far they were not optimal under general Bernstein, but this bound simply recovers it, and moreover we were able to prove the matching lower bound not only in the realizable case, but for general Bernstein with the beta fixed one. So this rate is more or less tied up to constant factors. For example, you can do similar ways, a corollary of the result, but when we work with L2 P entropies, which are more common in statistics, then considering, for example, when well-specified regression model, when f, x, and psi are all bounded, we can write down the following bound, which really mimics with the same more or less fixed point, which mimics the minimax rate for this problem. So, however, the ERM is not always optimal. So there are many cases when you have to use something else. You cannot achieve minimax optimality or optimal bounds using some empirical risk minimizers. And the idea is that you have to use other principles. So, for example, it's known that, once again, realizable case, that some ERMs converge slowly, even if we can compress to D points. So if we use sample compression, that in general we have more or less the same bound as for ERM, but the optimal bound is not given by any empirical process type results. It's given by some specific algorithm, and it doesn't have this log factor. So maybe we should assume something to make compression schemes achieve this optimal bound. Yes, there is one direction which seems plausible. So let's assume, and Andreas, let's assume some kind of stability assumption. Let's assume that our sample compression scheme is stable in the sense that if I'm removing a point that is not in the compression set, then the compression set of the subsample is the same. So the idea is flying around, and it appeared even in the book of Vapnik and Chovanenkis, where they were analyzing SVM. So, for example, support vectors for some hard margin SVM have these properties. And the bounds in expectation are also known, so you just do leave one out, and you prove that expected risk of a classifier built by the compression reconstruction pair has a very nice risk. But we went a bit further. We just decided to work on exponential tail bounds, which are really interesting to get. So the one of the more simpler result is that you can get this. So there is a more or less exponential tail for this for the output of this sample compression scheme. However, there is a multiplication instead of sum, so you cannot get the optimal rate. But if we require, or if we know that our reconstruction function returns or takes values in the VC class of dimension D, which is of order K, of the order of the size of compression scheme, then you can modify the output function to get an algorithm with a rate kilog K divided by N plus log N over delta. So modification works like you learn your pair of compression reconstruction on 3 independent samples and output its majority vote. So several words about the proof, and it's almost the end. So instead of exponential moments, we'll work directly with the moments of the risk, and it's not very difficult to prove this kind of bounds. But to work with this, we have to somehow to remove this multiplication and make it an addition as a sum of kilog K and log 1 over delta. So to do this, we use the technique which was used previously to analyze the measure voting over SVMs. And in this case, it's also sufficient to construct an algorithm with based on the initial bound, which has a sum here. So, for example, as a straightforward corollary, we have a polynomial time learning algorithm for learning in PAC scenario, for learning half spaces, with these guarantees that are almost optimal. And previously, these polynomial results were known only under special distributions and only for homogeneous half spaces. So, thank you very much for your attention.
So we have time for as many questions as you like. For one or two questions, please. So these majority constructions, they're pretty complicated?
No, it's very simple. It's just you have 3 samples of size n. You learn 3 SVMs and you output the majority vote over 3 so that's it. So the idea is that it somehow helps you or allows you to combine VC-type bounds where you know the nice concentration tails, but you have wrong logarithmic factors, with the bounds that do not have these wrong logarithmic factors, but that have a slightly worse concentration tail. So in some sense, by majority voting, so maybe it's a more or less mathematical trick just to gain from both worlds, in some sense, from both of stability, from the world of stability bounds and from the world of VC-type bounds uniform when you have the nice concentration tail. Okay?
So why only majority of 3?
So you can do it. I decided it's just for simplicity because for me it's more or less it seems that it's enough to get like something like this. So you can continue the work of or in the same manner as Hans Simon was working for ERMs. You can write it down that you measure vote over 5 SVMs and you get D log D, etc., etc. So you can do as many times as you want, but you'll in some sense lose maybe this, for example, polynomial time learnability because you'll need to learn them so many times in some sense. So that's for me it's a kind of trade-off.
So you can get rid of the log D by iterating this construction?
Yeah. So in some sense, yeah. There is a... But it's mainly... So this result is mainly about how to combine 2 types of bounds. So in some sense you have some better things you have from uniform convergence and some things you have from sample compression and stability. And then you just marry them together and get something interesting.
All right, so let's thank the speaker.
All right, with that, the conference is concluded. We would like to thank all of you again for staying to the very end, and also another round of applause for the organizers, the local organizers, and everybody else. Thank you. And see you next year in Sweden.